I'm Maxim Fateev. I'm staff engineer at Uber. I've been with Uber over 3 years. And before that, I was in various companies and 8.5 years at Amazon, and where I was a tech lead for the simple workflow service. And a very clear relationship between, at least from ideas and even APIs, from Cadence to simple workflow service. And also worked on a backend for a simple queue service. And I really appreciate you guys being here, because it's not about machine learning. It's about workflows, and workflows are not as sexy as and interesting, like at least for some people. But I think here I want to kind of show you that this is not like average workflow engine. It's actually the tool which every engineer can use, at least when building distributed applications. I will focus around use cases just to kind of show how this tool can be used to build real-life applications. So, for example, when you press a button in your mobile app to tip a driver, we need to make sure that this transaction happens and money always exchange hands, and even in presence of failures, and also Uber scale. And underneath, it's actually pretty straightforward. We don't do transactions to transfer money from one account to another. We always do a bunch of API calls to different services, because Uber internally uses servers and architecture. Obviously, in this greatly simplified form, it goes back to practically 2 API calls: get money from one account and deposit money to another account. Problem is that you cannot just go and write such code in your service practically implementation, because you will have failures. And for example, if you debit it and then you try to credit and it fails, you end up in an inconsistent state. We all know how to solve that. And a very standard approach is just to put queue in front of this handler, and then queue allows you to ensure that even if this handler fails, the handler is retried. Obviously, you need to assume that all these calls are idempotent, but eventually it will kind of do the right thing and do the transfer of the money. Obviously, it doesn't work very well if you have permanent failure. For example, account ID is not there. Then you need to practically start complicating this implementation a lot. Other problem with this approach is that using queue is that queues are actually not very friendly for long-running tasks. If you have a task which runs a few seconds or even a few minutes and you don't have very high rate, queues are okay. But as soon as your task can have tens of minutes or even hours, then queues are just very bad technology to implement such tasks. The standard solution is to add more queues. And everyone probably seen this type of architecture in one way, one form or another. Practically, you end up creating these graphs of queues. You take a message of queue, you have a handler, it does something to it, calls some services, then creates new message, puts the next queue, or maybe even multiple queues if you need to run things in parallel. And one problem with this architecture is very hard to troubleshoot, or even from business sense to like get question, what's the status of my transaction? And answer is, yeah, we have message in one of these 10 of queues, and maybe it's not lost, and we don't know. And if you actually have some production problem, it's even harder. So standard solution is to add database. So practically, every time you get message out of the queue, you transform it, but you also go and update state in your database. Then you can query your database for statuses and use it for troubleshooting. A problem is that usually queues and databases don't share transactions. And these days, nobody runs two-phase commits across them. So practically you end up with all sorts of race conditions. Most obvious one, you put message in the next queue, and then database update fails. And if you just use the database for statuses, it's okay. Okay, you get stale information. But in a lot of cases, you actually use this database information to process message in the next step of your pipeline. And in this case, you can end up in very bad situation when you get message and the database didn't go through. Even if it didn't fail, it could be that just update takes longer than deliver message to the next stage of your pipeline. Obviously, you can try to reorder those statements and do update to the database first, then put message in the queue. But you obviously start running the kind of similar race conditions. And it's not like theoretical. I actually have seen a lot of production level code which actually doesn't deal with these race conditions. People can, okay, we kind of pray that in most cases it doesn't happen, and if it happens, we will deal with that offline somehow. And usually you get frustrated customer making call to the customer support. So going back to the original kind of business level problem, it would be super nice if you could just go and write this code as failures don't exist. Problem is why this code is complex, because failures do exist in our system. So if you debit it and then credit fails, you need to do something about it. And this is exactly what Cadence is about. Cadence is practically allows you to write your code in a way that you don't need to deal with failures. Obviously, I'm oversimplifying. I will go a little bit more about it. But the kind of core idea is that if you write this function in Cadence, and even if this operation takes long time, and for example, long time, really long time, like 5 months, and you say debit rider, and this debit rider takes 5 months, you still will have a line of code which is blocked on that exact line and waits for that call to return. And this is disconnected from the actual process, because if this process fails, Cadence will make sure that it's reconstructed in exactly the same state. And when by state, I mean not only data, but also practically all local variables, threads, and so on. I'll show how it looks like if you use, for example, Java SDK. But this is kind of the main value proposition. So it's not like your workflow engine in the sense that people are used to how we define process and bunch of like graphs and so on. It's practically this virtual object, which can have state, but it also can have processing and multiple threads, and we fully preserve that independently of the failures. Obviously, the calls like to credit and debit can fail, but this is more like business level failure, which you need to deal with. We came from workflows, so we kind of use workflow terminology. In workflow world, we kind of separate all application into the 2 types of entities. Practically, we have activities, which are kind of similar to tasks if you're using queues. Practically, this unit of work doing something more or less atomic, at least from workflow point of view. And we have workflows which orchestrate those tasks. Ideally, tasks, they act on external world. So they practically, they're something like service call, database operation, the whole MapReduce job, anything, which is practically interacts with external world. And workflow is code which contains state and can use those activities to practically influence the world. But workflow doesn't make, for example, API calls directly. It always acts through activities. So it kind of orchestrates them. So Cadence Activities, again, as I said, they're kind of tasks similar to queues, but they have some features which are actually make them much more powerful than usually people are used to like using tasks. So first, it's any application-specific code in any language practically. They can be very long-lived, so there is no hard limit how long they can be. I'm saying that you can have activity for a month or more. They can heartbeat, because if you want to get failure faster than the timeout of this task or activity, which can be very long, you will, for example, if it can take 5 days, but you monitor it constantly and you heartbeat, if it times out, heartbeat doesn't come, it will time out faster. They can be implemented asynchronously. What I mean by that is, obviously, if this activity runs for 3 months, you cannot tie it to a single thread or process. So you can actually complete it from a different process a few days later. For example, sending an email to the customer, getting a reply can be modeled as a single activity in this system. They automatically retried according to specified retry policy, exponential retry policy, and these retries are practically unlimited, can be as long as you need. One important feature is that you can route the specific processes. So if you have workers, multiple workers, you can actually target specific worker if you need. For example, very common scenario is you need to download some data set and then transform the data set and upload it back. We have multiple examples internally. For example, you take your ML model, you download it and it's big and it's cached on some host, but then you do a lot of operations on that, for example, updating that or retraining that. So you need to route all tasks which operate on the data model to that specific host. So first activity can hit any host in your cluster, but then all others should be routed there. So Cadence support routing tasks to specific hosts. They internally dispatch for queues, so it means that when you make a call, it's not a direct call. So if you're, for example, worker which runs this task is not running, you still can make a call and it just will be queued in the queue. And then when it comes back, it will be processed. So it kind of, internally, we do use queues. And I'm not saying queues are bad. It's just that we hide it from you. From your point of view, it just looks like API call. And then you have certain limits. You can actually, for example, if this activities makes downstream call to some service, and this service has some rate limits you have to obey. For example, it cannot sustain more than 100 requests per second. You can practically just rate limit that particular queue which we are using to execute. And then even if you're making these calls faster, a system will make sure that the tasks are not dispatched faster than the rate limit. So I'm showing Java API. We also have Go SDK, and it's possible to add other SDKs. For now, we have Java and Go SDK. In Java, activity implementation is just interface and implementation of that interface, nothing more. So practically you define interface of your activities, and you can have more than one interface, obviously, or you can have more than one activity, which is method practically of the interface. And implementation is just plain Java object without any, you can, as you construct this object to register with our system, it means that you have full control over the dependencies of that object. It can have database connections, service clients, and so on. Practically anything you need, you can inject there, and then you can just register with our system. Obviously, this object should be reentrant because it's shared across all activity executions in the system at the same time, at least on that host, obviously. But there is nothing special about them. It can be any code, application level code. Workflows is actually much more interesting. So they are what I call virtual objects, and we go a little bit more about that. But basic idea is that you write your code as this code lives in a single process, and there are no failures. You just say, okay, this is my object. It has this state. It can have internal fields, whatever, logic, threads, and so on. But I don't link it to a specific process in the sense that this object, that's why it's virtual. It can migrate across processes if necessary, or be passivated if it's waiting on some timer for 3 months. But when you write code, you don't need to think about it. From your point of view, it's kind of this magical object which never dies. It's transactional, so all these race conditions I described between queues and state transitions do not exist in Cadence. For example, it's impossible to change the state of this object and schedule some activity, and then the activity, for example, task is lost, or otherwise task activity is invoked, but state is not, there is no state transition. So this kind of things, all state changes in invocation for external services are transactional. Obviously, activities themselves are outside of those transactions. So it's a distributed system. So then when after invocation happen, then we guarantee that you will get error or timeout, but we cannot guarantee that activity's execution because it's just your code. Workflows also can then orchestrate activities, which that invoke them, and then they can also react to external events. For example, very common at Uber, every time, for example, trip finishes, we get a trip completion event in some Kafka queue, and then you want to react to that. And we can actually have workflows, which are these virtual objects that receive callbacks every time trip happens and actually update their state or react to them somehow. So they're stateful, and it includes local variables and stack. Practically, your code is, all the state of the object is preserved. It's queryable, so you can actually run queries on that object and get any state out of that if you need to. They can be very long-lived. And this is very big difference from the standard kind of people used workflows. So people think workflow is a process. Like you start there, you do these tasks, and then at the end it's done. In our world, as this virtual object, you can have this object always live. For example, there are systems at Uber which have object per rider or per driver in our system, which is like we have tens or hundreds of millions of them, of those objects potentially. And this object is always live, it always exists. And then it just handles requests or does something related to that. So it's a very different paradigm from kind of process. It can execute things and it's in a sequence if necessary or in parallel, but it always can exist and have a long life cycle. So technically you can have one, for example, object to manage whatever in your system, I don't know, customer. And it always will be responsible for making sure that customer interactions are like going through that object. I mentioned durable timers here just to make sure that you can actually do things based on time. I'll show how it makes for API. So workflows in Java API, you just use kind of similar approach. You define an interface. The only requirement is the annotate method, which is entry point of the workflow, which you use this method to start practically this signature to start workflow from outside world, for example, from your UI or from like whatever application. You will just call that signature. And then you need to annotate this workflow method. And obviously you need to have timeout. It's just when workflow if it doesn't make progress, it will be automatically terminated after that timeout. There is no limit how long it can be. If you want a timeout of, we have customers which did timeout of like 30 years. Then one of their workflows ever timeout. It was kind of interesting to see. And the implementation of workflow is just implementation of that interface. What's make it interesting is that to invoke activities, it uses this so-called activities tab, which implements the activity interface, which we saw earlier. So practically you just say new activities tab, and you get this instance of this client, connectivity client, and you make calls on it. So this looks like just normal Java code, which invokes some methods on this activity object, but behind the scenes, a lot of things are happening. So most important thing is that when you make a call, it actually creates a task, puts an internal queue inside of Cadence, and then activity worker pulls from that queue and gets the task to execute. Other thing which happens, it preserves its state. So it means that, for example, with debit, as I said, call takes a few days or like even months. You don't need to change anything. Your logically, or practically, your thread of control will be blocked on that line. And then like it comes 3 days later, it goes and continues. And it's not linked to any specific process because again, process can come and go, you can do restarts, you can do deployments. It's still, this object still will be in that state, at least logically. And you, as a developer, this is the most important feature, you don't need to think about failures of that particular process. It kind of completely disconnects you, so you don't need to deal with those failures. Obviously, again, activities can return errors. Other feature is that we do kind of automatic retries, and you can configure them for any activity. All you do is just specify retry policy, and you attach that retry policy to the stub. And so all invocations on that stub will follow that retry policy. And again, it can be as long as you need. In this case, expiration of the retry is set to 1 day, but you can set it to like to a year if necessary. That is kind of how you get the automatic retries. Other thing which I kind of mentioned is that obviously, for example, if you debit money and then there is a failure crediting it, you need to deal with that. So how you would do it here, you would just catch the exception. And obviously I specified kind of simple, but the basic idea would be you will write what's called compensation logic in this case. And think about it, we are not dealing here with failure of processes or like queues or whatever. It's your business logic. Business logic is there is a permanent failure crediting to the destination account. I need to deal with that. So I will write my compensation logic to deal with that. But this is not, you're writing this error handling code not because of, again, hardware failure, because it's your business logic kind of failure scenario. So far, I kind of showed you use case where most important feature of Cadence was that it guarantees that a certain business process will execute no matter what happened, right? From the beginning to the end, and it can be long running. So other important feature of those objects that they can have state. So it's not only processing, it's not only kind of a sequence of function calls, you actually can have state in those objects. And this is this driver reward study is kind of demonstrates the basic idea is that we have various scenarios inside of Uber which are similar. For example, recently launched loyalty program we have. It does exactly that you have driver, which is a part of loyalty program. And then every time a trip, for example, happens or something happens, this object kind of accumulates additional data about that and then evaluates if, for example, if he goes to next level of whatever loyalty program, and then can perform certain actions on external data sources based on that. And the standard way to implement that would be, again, you put a queue, and then you have some sort of timer service, so like a job scheduler, which will invoke your callback once a month, because, for example, in this case, you need to revalidate that, in this particular example, once a month, your eligibility to that program. And again, this solution kind of works, but problem is that it will need to deal with these race conditions and failures. And as you make a lot of API calls, you actually very easily end up in inconsistent state. Other problem is that invocation of activities, all these retries are actually pretty hard to do if all you are doing is practically listening on the queue or having a callback, because you want a kind of exponential retry and so on. The Cadence-based implementation is just, again, it's just an object. You will define driver rewards workflow, and that workflow would have just state as fields. Well, local variables are also state, but in this case, just fields, and they're int type, but there is not really constraints what type it can be. So you can define your own structure. You have your objects. This object can have, so practically you can use all object-oriented techniques. You can actually construct your workflow as not just one object, but as many objects as necessary. You can construct it at runtime, so on. So that's why these kind of workflows can scale to any complexity. Like if you take, I don't know, if you're used to like existing solutions which use YAML files or like UIs, it's very good for hello world example, but as it goes beyond like 50, 100 tasks and you need to do some complex error handling logic, they become unmanageable. And this is code. Like all we know that yes, code has complexity, but like we write million lines of code, systems which have millions of lines and they're still manageable. This why workflow of any complexity can be implemented using this approach. And so we have state and we have practically callback on trip, which is called every time trip happens, trip completion. How it works from Cadence point of view. So we have a different type of method, which you need to annotate as signal method. So signal is a method which is practically a callback into the workflow from outside world. And it can be anything. It's practically any external system can go and call an API, practice a signal workflow. It needs to give ID of that workflow. It's actually important. One thing I didn't mention is that you give usually to workflow this object business ID, and we guarantee uniqueness of that. So practically, if there is one workflow per driver, we guarantee that will be only one workflow per driver. And you cannot start, like if you make this call multiple times, it will go to the same object or it will fail if you're trying to start it again. But basically, you will just go and sense these signals method. We guarantee they're not going to be lost. And this callback will be called. In this case, we just update those variables in that callback. We also have query method, which is, again, a way to get information out of that object. You call this query from outside world, from UI, from CLI, from anywhere, and you can practically get any information out. Again, it returns just float number here, but can be any data structure you want. Obviously, it should be serializable in this case because it kind of goes over the wire. Other thing, you can have as many as you need signal methods and query methods. That doesn't mean that you can have only one of the type. So if you can have different queries, these query methods also can have parameters. So you practically can actually query parts of the state if necessary. And how do you tie that together? So practically every workflow should have at least one workflow method and it can have multiple query and signal methods. And this workflow method will just use these fields or data, whatever is in workflow, to implement its logic. And in this case also, we use just one thread, which is main thread of the workflow, but you can start new threads, you can do parallel executions, you can do asynchronous stuff, you can call activities asynchronously and get promises back, and which are similar to Java futures and which don't get of them blocks. So you kind of get standard to kind of Java primitives. You also can do async with kind of similar to completion stage interfaces, so if you're in your code. And in this case, this code, if you look at just loop, which will go and check if this promotion is expired, reset variables, and then sleep. And look, this is actually normal production code. It's not a joke. You actually can go and do, say, sleep for 30 days, and then you will just, after 30 days, this line will unblock and continue. So practically this way, you don't need to deal with, again, you just implement your business logic directly. And you don't need to map that to these underlying systems. The Cadence kind of hides all this complexity from you. So other use case is a little bit closer to what people are used to think about workflows, is that inside of Uber, we had existing system before even Cadence was created, which modeled workflows as using UI tool. And this is mostly tailored to the non-developers. We have a lot of people who actually operate our business, and they practically reside in every city. And they create these workflows based on their specific city requirements. And there are like thousands of those like UI-driven workflows. And the model of these workflows is very simple. It's just a bunch of nodes connected for it's practically DAG. And every node has outgoing edges, and every edge has associated conditions. And practically, when you get an instance of that workflow, you just get one node can be active at a time. And you practically, all state of the workflow is just active node, nothing else. And plus ID of the entity, which is like a driver ID, for example, or rider ID. And then when you get new external event, you match that entity to specific instance of that workflow. You evaluate conditions, and evaluation of condition, because there is no state inside of workflow, is a bunch of RPC calls to external services. For example, condition can be driver has more than 100 trips. So it will go and make a call to the special service, which will return number of trips per driver. evaluate this condition, and then if condition evaluates to true, it will just transition to the node, first node which actually got that. Very simple model. Problem is that, and then like this node has some actions scheduled to that. It can be send email, give incentive, and so on. Problem is scalability. We have a lot of entities, and we also have pretty high rate of these events coming. So if you do, and other interesting thing that we have on average 50 workflows, these workflows, like UI workflows per entity. So if you have like 10K events per second coming and you have 50 workflows on average, so you practically get half a million condition evaluations per second, and most of them actually are RPC calls to external services. So practically we kind of have this workflow engine which needs to sustain this rate of execution of this kind of RPC activities and also create like large set of actions. If you like used to like normal, most of them just, you cannot like even imagine using them for these rates. And initial implementation was using the kind of standard approach. It just was you listen to those queues, having callbacks, going to database, loading state for each workflow, updating the state, evaluating conditions, saving it back. So it worked. Unfortunately, it was almost impossible to deal with failures to these services because as all your practically state is in database, you practically need to create very complex state machine to practically manage all these retries and also make it efficiently. And also as our database was Cassandra and we used practically just quorum writes and reads, and you can actually lose data when you do quorum writes and reads and updates because due to race conditions, practically it was actually getting situations when workflows can get stuck or don't make progress and so on. So it was actually not guaranteeing the execution. And we actually migrated that to Cadence, and practically these workflows became practically just implementation using our SDK, Go SDK. We just practically wrote interpreter of this graph using our SDK. And we were able to practically just maintain the existing UI implementation, but at the same time, they didn't change their UI and they just implemented this underlying component, and then they practically got run it on top of Cadence. And main advantage of that is, first, all retries became practically very easy to do. As you saw, you just specify retry policy, and Cadence guarantees durability of all those retries, make sure that they happen. Other part is that the way we did it, we actually did some interesting trick. We actually created workflow, not per like their UI workflow, we call them campaigns, but we actually have one workflow per entity. So we have workflow which has like per driver, right? And internally it has all 50 UI workflows as just variables, as like in their list. And then we get event, we just iterate through them in memory and apply them to that. And this way, what happens is that our database load is proportional to number of events, not to the number of campaigns multiplied by number of events. So there was actually, we actually talked to some other like companies out there, for example, IoT guys. They have similar problem. They have a huge number of devices, and they have like a lot of actions possible per workflow, per device. And they have similar problems that they get these like events, relatively high throughput of events for large number of devices, and they can just implement that using this approach, for example, for the IoT very, very efficiently. Another part is unified workflow engine. And this is just graph from our test runs, but kind of to show that we actually can sustain this load. There is nothing super interesting about them, it's just that we do scale. And it kind of goes to the point is that we position Cadence is not to like, because people usually think about workflows as something like for data pipelines or for kind of low throughput, low traffic thing. And for us, you can do that, absolutely, no problem. You absolutely can do data pipelines using this approach. But the most important part is that you actually can do it per business transaction, per business entity. That is kind of our goal, is to replace all these ad hoc workflows, which developers do every day using queues and databases. Every time we, like, I see that if you migrate to Cadence, it greatly simplifies that architecture. It's very, very common. And usually what happens is that we start from, so we get a team, and this team comes and says, oh, I need to replace one task. We had a queue, and our queue, for example, has some issue, it's long-running task. We needed to replace this one task with workflow. And they're like, okay, can you describe your use case end to end? And when you end up, the use case is actually 50 tasks or like 15 tasks, and they're complex, and they have hard time actually maintaining the system. They say, okay, can you migrate the whole thing as a single workflow? And it's a revelation for them because they never thought about their system as a workflow. They just thought about it as a bunch of tasks. So that is one of the problems, like with adoption of Cadence. For most people, it's actually a paradigm change. It's not about because it's not like different type of queue, or it's not fast or something. It's a completely different way to build your distributed application. So other thing is that Cadence is a platform. So the idea is that we support Java and Go SDK, and we can add more SDKs in the future. But other important thing is that you probably can take any existing workflow definition language, VPMN, like AWS step functions and so on, and you can make it run on top of AWS. So this slide is like future vision. It's not that we have all these languages already supported. Don't take it take it as a grain of salt in this. But it's absolutely possible. We internally have multiple implementations besides the one I showed you, Flow one. When existing workflows, engines were migrated to Cadence. And the main benefit is that we have one engine, which inside of Uber, it's one team owns it, and it's practically a hosted service the same way like AWS service internally. So anyone who wants to use it just uses us. And you practically eliminate all these multiple workflow engines, because very frequently what happens is that people start from workflow definition. They think, oh, I want this YAML workflow definition, or I want whatever, JSON or XML, VPMN. And the implementation is afterthought. It's very rarely scales very well. It's hard to maintain and so on. And this way, even if your company has 50 existing workflow engines, you can migrate all of them to run on top of Cadence. And you have just one workflow engine, scale workflow engine, but still do not argue, for example, which workflow definition is better, or you can support legacy workflows. That is kind of our vision, is start supporting more and more languages, and especially when open source people start contributing, we can absolutely start supporting more. Other part is DSLs. Sometimes for your specific domain, there is very well, like domain specific language makes much more sense than generic just code or generic workflow definition language. In this case, it's very easy to add DSLs on top of Cadence, and we are putting more effort to make it even more seamless experience. That is kind of our vision, is that first our goal is eliminate all ad hoc workflows, and we are at Uber practically we are right now de facto standard to all asynchronous backend logic. And then other goal is practically unify all existing workflow engines, at least inside of Uber, under one practical platform. So use cases, we have like 50 plus teams using us right now. But these are kind of some notable use cases. I'm not going to spend like too much time going into them, but basic idea is that they're very different. Practically everything which is backend can be. We have CI/CD pipeline practically rewritten fully to use instead of Jenkins to use this infrastructure, because just Jenkins didn't scale for us. We have customer support workflows which involve humans. At the same time, we have like freight business, and they model their load. Load is like trip for them, practically as a workflow to do certain state transitions there. We have people in data using us, for example, to manage data set like life cycles. For example, you have some big data set and you need to replicate that or whatever. So it's you create just this object which manages the life cycle and makes sure that deployment system. We have deployment system which practically deploys our services, and it uses the Cadence. And most common example, just cron jobs. People just want a reliable timer. And this is a very simple example, but it works very well. So going back a little bit to higher level, every one of us has kind of toolbox of different components we use when we build our applications. Well, obviously, we have request handlers in the form of microservices. So these days, maybe Lambdas, serverless, actors. We have storage, databases, caches, queues, job schedulers. So Cadence is actually interesting. It actually has internally, we have all of that. We have all of these components. But we hide 90% of this complexity from you and let you practically write your business logic, focus on the business logic, and write your scalable, like distributed applications, a bunch of these high-level objects which can communicate to each other asynchronously and act on external world through tasks. And still have persistence, durability, like longer-running timers and so on, but on the form which is much more friendly to the programmers. That is kind of our value proposition. So to summarize that, it's what is Cadence? It's a high-level way to build and distribute applications, and you focus on business logic, not plumbing. It's large scale, so you can have billions of entities. You can do very large rates. It's highly available. It's not only host failures. One thing I forgot to mention is we support cross data center, or practically in our case data center, but if you use AWS technology, cross-region replication. So you practically can have one cluster in one region, another cluster in one region, set up asynchronous replication between them, and your workflows will be active in one data center, and then you can fail over what we call domain, which is like namespace. You can, every team has its own namespace because we are multi-tenant service, and you can fail over that domain to another region, and your workflows will continue there. With caveat, it's asynchronous replication, but it's actually like, it was main requirement, for example, inside of Uber, we couldn't be used by most important services inside of Uber unless we have, we can sustain full data center outage and still continue working. So you can unify all your workflow solutions because you can practically run any workflow definition language on top of that. So you can do your own DSLs, and it's open source, so you can use it. That is out there.